Good morning, everyone. So people are still coming. It's 10 a.m. and we have to start. So everything is recording. Yeah. Today we're going to talk about the electric flux. All right. What is that? We started discussing in our lecture, but we haven't finished it yet completely, right? So tomorrow I will finish it, and then, of course, we will start introducing Gauss's law, because we need this tool in order to introduce Gauss's law. So we need to understand the idea of electric flux and how we can calculate it. We need to understand it very well, right? Because we will need it in a Gauss's law. Right. Okay. So before I can write down what is electric flux, right? So we need to refresh what is the area vector. And then, because we need it, we need this very strange, unusual vector in order to simplify notations of the electric flux, right? And we introduced that in the lecture. Let's just quickly refresh. So if you have a surface, doesn't matter which surface, circular, flat, or curved, right? So you can introduce the area vector. And the area vector, by definition, perpendicular to the surface all the time. It doesn't matter how you position your surface, that area vector is perpendicular. By definition, it's just basically a mathematical tool, right? And the mathematicians introduce it in this way because it helps to simplify notations of many quantities, right? Perpendicular, and the magnitude of this vector, the magnitude of this vector equals to the area. A very strange, very artificial vector. It's not like velocity vector, acceleration, or force vector. It's very, very strange. I keep using this word, right? Okay, so let me write that down. So if you have, for example, some surface, okay, let me make it small, some surface, right, of area A, right? And then, yeah, we can introduce this area vector, which is all the time perpendicular. So that angle is 90 degrees, right, between the surface and the vector. Right? And so two properties, right? So let me first write the area vector. Area vector, and then A area vector perpendicular to the surface. Okay, let me use A surface. All right, and then absolute value of the area vector equals to the area. Okay, I can even write area of that surface. Okay, so, and after this, yeah, we can introduce the electric flux. So let's imagine that, for example, this field, right, field with some electric field, right? So a bunch of electric field lines we can draw. So there is an electric field, and if you have a surface, any surface, exposed to this electric field. So of course we can ask a reasonable question. So what is the number of electric field lines crossing this surface? So electric field lines crossing this surface. So we can ask the question, so what's the number of electric field lines crossing that surface? And mathematicians introduce this tool which allows us sort of to count that number. Right? But again, the meaning of the electric field lines, or electric flux, it's a number of electric field lines crossing a certain surface. Okay, so now let's start introducing that, and we're going to introduce the kind of two formulas for the electric flux, but it's just the same. The first one for the simplest possible case, and then the second one for the most general situation. Let's start with the simplest possible case. Right. Okay, I will put here a new bullet. Simplest case. What can it be? A uniform electric field and let's say a flat surface. uniform electric field and flat surface. The simplest possible situation. Right, so let's say if electric field, which we wrote it, E is uniform and area is flat. Area is flat. Okay, in this case, I can draw some surface, for example, something like this. Right, so that's our surface A. Electric field, uniform. Okay, it somehow crosses over there. I just draw a bunch of lines, right? So uniform, all right, electric field, let's say E, right? And now, in order to introduce the formula for the electric flux, let me draw the area vector. Now here, area vector. Let's say this surface is slightly tilted. Let's say this is area vector, A. Right. So let's say I've drawn at this point, right? So the surface is slightly tilted maybe, right? So in this case, the flux, electric flux, can be written as a dot product between the electric field and the area vector. Right. Again, this is the simplest possible situation when the surface is flat and the electric field is uniform. Right. And today, most of the time, we're going to use actually this formula. We're going to use this formula. All right, so it's the first simplest case, and now let me separate this, put a next small bullet, and let's look at a more general situation. What if a surface is no longer flat? For example, let's say this is not a flat surface. You see it's curved completely. It can be any complicated surface. And let's say electric field is no longer uniform. Right? We will discuss it tomorrow sort of in details, but now I will just write down the formula which we need to calculate the electric flux in those cases. All right, so what if now E is not uniform and area is not flat? Okay, okay, let me draw some arbitrary situation. Let's say this is my surface, right? This is my surface, kind of complicated, right? And the electric field kind of also not uniform. Okay, so what we have to do in this case, we will slice this surface into many parts. Right. Take small patch. With the area vector. Now, of course, I will have to draw a area vector for this small patch, and it will be labeled as dA. And of course, there will be some not uniform electric field, right? So maybe something like this. So let's say this is our electric field. Right. And now the flux through this small patch, we will discuss that in details tomorrow. It will be just a E dot dA, E dot this small surface, and then we'll have to take that number, then calculate next number through the next patch, then flux through the next patch, and so on, and keep adding those small fluxes. If you add them all up, you will end up, of course, with integral, and that will be the total electric flux crossing this surface which is not flat and exposed field which is not uniform. Strictly speaking, it's a calculus 3. These integrals are not trivial, right? But you will see. We will actually be evaluating those integrals without actually taking them, right? So yeah, it's calculus 3, but you don't need to know that fancy stuff. At some point, you will learn how to handle these surface integrals. For now, we need them, we will use them, and we're not going to take them. You will see how we're going to handle them tomorrow. Okay, so, but anyway, for now, That's the expression, again, number of electric field lines crossing this surface, right? In the case when surface is not flat and electric field is not uniform. And this formula is just a special case of that one. If E is constant, take E outside of the integral and you will get just the E dot A. Okay, so that's the second part, no, the third one. And now sort of the last one, the easiest one, which you knew, because now you see we have dot products, scalar products. Here you see the solid dot product, scalar product. Here the same, right? Solid dot, it means scalar product. Let's refresh quickly. How can we calculate scalar products? So let me write, recall a scalar product. Because we will need it in several places, actually quite often. Then we will recall vector product also. So scalar product. So let's assume that we have two vectors, A and B. Right. So how can we calculate a dot product between these two vectors, A dot B? There are two ways. First one, you just take absolute value of this vector times absolute value of the second vector and times cosine of angle between them. Cosine of angle between them. And now you need to be careful, right? How can we find the correct angle between two vectors? You need to position tails of both vectors at the same point. Let's say this is tail of the first vector, this is tail of the second. You need to position tail. You need to position their tails at the same point. And the angle less than 180 degrees is the correct angle. So this is the correct angle. This is correct angle. So the way I drew these two vectors, this is the correct angle because the tail of vector A is over there. The tail of vector B is also the same point. So this is the correct angle between these two vectors. So let me show. This is theta, correct angle. Right? So that's one way of finding dot product. Or if you have vectors presented in the component form, then we can calculate the dot product or scalar product in this way. You multiply corresponding components, x components, y components, and then z components. Multiply the corresponding components and then add them all up. Of course, you will end up with the same number. It doesn't matter if you use this or the second option, then the answer will be exactly the same. It can be easily shown mathematically. So ax, bx, you see, just the product of the first of x components, then product of y components, and then product of z components, and you add them all up. So first option and the second option. So that's what we need for today. And now let's start looking at examples. Again, if something not clear, just tell me. We will talk about this, as I said, tomorrow more. Yeah, that's the review. And chapter 24, yeah, it's written. Problem 10. Let's start with problem 10. 24, 10. All right, so what do we have here? Again, we will have to calculate fluxes all the time today, right? So in order to have flux, electric flux, you need electric field and you need a surface, right? So let's assume that our surface is this. All right, I'm just trying to estimate the amount of space that I might need. So this is surface, A 10 centimeters, and here B also, yeah. So basically it's a square, 10 centimeters. So yeah, we have surface. All right, electric field, strength is given. Electric field, absolute value of the electric field, so the strength is 200. And units, you remember there are no special units for the electric field, so just newtons divided by coulombs. Newtons divided by coulombs. So that's the electric field. So this surface is exposed to the electric field, and there's another piece of information, some angle is given. Let me draw that situation because it's easier to show that angle on the piece of, on the drawing. Right, so let's see. So let's say this is our electric field, right? And you see it's constant, right? Electric field is constant. So it's a uniform electric field, and the angle which is given, this angle is given. So let me draw it, this one. Let me draw this dashed line. This dashed line lies in the surface. And the angle which is given is, yeah, this one. 30 degrees. So let me make this solid. Yeah, it's better. So that's it. Okay, let me label that angle as phi. So phi is 30 degrees. So we need to find the electric flux. So what we need to find, again, number of electric field lines crossing this surface, electric flux. Then in a couple of months, or maybe less already, we will introduce magnetic flux, and it will be very, very similar. So the idea of fluxes, it's okay, popular, I would say, important in physics, right, in math, and in many other fields. Right. So what? First of all, we need to understand, because physics is quite simple. There is an electric field, there is a surface, so there must be some amount of electric field lines crossing that surface, right? So we just need to understand which option is better to use, this or that. Obviously, we have a flat surface, uniform electric field, so obviously we need to use this. Right? We need to use that. Right. So E is uniform, A is flat, so we can use the electric flux equals a dot product of E and A, right? So we just need to use the first option, this formula, right? Let me frame it. And so now, dot product, scalar product, and now we need to decide. Of course, we will have to evaluate the scalar product. Which option is better to use? Option number 1 or option number 2? Maybe let me put here, so it's a number 1, and this is number 2 option. You see number 1 and number 2. I should have left more space to write it down. So which option is better to use? Of course, either of them would be correct. But if you try to use one of them, it will be easier, easy calculations. If you try to use the other one, it will be more complicated, all right? But of course, in both ways, you will get exactly the same answer, exactly the same number. And usually most of the students give me the correct answer in this point, right? So of course, option 1 is better to use because it's more convenient when you have magnitudes and the angle. If components are given, then of course it's much easier to use that. Right? So, and in this case, we have magnitude of the electric field. We should be able to find a magnitude of the area vector. Right. So obviously, this option we will use. Right. So, of course, I will use electric flux will be equal to E, A, and cosine. Okay, that's on purpose I stopped. Every time I stop at this point, because now we need to decide which angle I have to write here. And quite often, students give me the wrong answer. Because again, usually I ask that when we were in class, of course, I would ask at this point all the time, right? And I wouldn't move without getting the answer. We have to be careful at this point. Plenty of mistakes at the beginning, and then, of course, students stop making those mistakes. So what's the meaning of this angle theta? You remember I mentioned about how can we find the correct angle between two vectors. In order to find the correct angle, you need to position tails at the same point, right? And the angle between them is the correct angle. So let's draw vector A, because right now the second vector is not on the picture, not on our picture. The second vector is A vector. So of course we cannot tell which angle is correct if we don't draw all of those vectors, right? So let's draw it. Of course you can draw it anywhere. You can draw it here from this point or from that point, but of course, as I told you, in order to find the correct angle, we need to position both vectors at the same point. So let me draw vector A from the point where from this point, so I can, so my vector A and this vector E will work together. Right? So let me draw it this way. So this is my area vector. Okay, it would be absolutely correct if somebody picked area vector downward, because for the surfaces like this, there are any restrictions in terms of direction of the area vector, except for it must be perpendicular. So if you pick area vector downward, it would be correct. But I'm not in the favor of that direction, because in that case, flux will be negative. Again, it's not wrong, it's absolutely normal, right? But I usually prefer to pick area vector somewhat in the direction of the electric field, right? So that the angle will be less than 180 degrees. Less than 90 degrees, right? So let me pick this way, area vector. And now, obviously, these two vectors, the tails of these two vectors are at the same point. So this is the correct angle. Let me use blue, blue, I've used it. Right, so let me use black, this. So this is the correct angle which we need, that theta. So it's an angle which complements 30 degrees to 90 degrees. Right. So that is the correct angle. And quite often, quite a few students don't see that at the very beginning, and they just grab the first available vector in the problem, hoping for the best, right? So usually they grab 30 degrees, plug it here, and of course that is not correct. And very often on the exam, first midterm exam, final exams, occasionally I probe that to make sure that you guys still remember that. Find the dot product of flux, right? And of course I give the angle, which shouldn't be used in the calculations, but you should be able to find the correct angle. Right. So in this case, obviously 60 degrees is the correct angle. Okay, let me write over here. I will use theta, right? And then I will open my explanation box and show that theta equals 90 degrees minus phi, which is 90 degrees minus 30 degrees, gives us 60 degrees. Even, of course, don't feel bad, because even graduate students, right, or up on the graduate level students in my classical mechanics course sometimes forget about that, and they make these silly mistakes. Okay, so now we can write explicitly. Basically, this is the only sort of point where mistakes are possible. So electric field, 200 newtons per coulomb. Area vector, again, don't forget to convert to meters. A and B don't use centimeters. So it will be 0.1 meter times 0.1 meter. So you remember the length, the magnitude of the area vector equals to the area of the surface. Right? And then cosine of 60 degrees. Cosine of 60 degrees I remember by heart. because when I was undergrad students, our professor used only angles 0, 30, 45, 60, and 90 degrees. So I remember by heart all of them. So it's 1 over 2, right? And we will get, as a result, here 1 over 100. 2 zeros will disappear. We will have 2 over here, and then 1 over 2, so we will get just 1. All right, the flux will be 1. And for the electric flux, there are no any special units. So whatever you see in the formula, newtons divided by coulombs times meters to the power of 2. And m squared divided by coulombs. Right? So that's the value of the electric flux. Right? Again, physical meaning, you can think of this as a number of electric field lines crossing certain surface. This surface, not certain, this surface, right? Right, so today's problems are reasonably straightforward. No tricks, right? Not much. So the next one, somewhat similar. All right, we will look at the same flux, at the flux from slightly different angle. All right, okay, I don't feel like erasing this. I need this, so I have to start erasing that. Okay, give me a second. Again, if something not clear, start talking. Yeah, my speakers are on. Right. Okay, I will start erasing. So now it's 12a, the same chapter. 24, 12, and part A. In homework, you're going to have both, I think, part A and B. Again, flat surface. And electric. Okay, let me start with the surface first. Right. So let's say this is z-axis, y, and I need more space. Okay, it's time to erase this, and x. Okay, let me make it slightly longer and increase the angle. Okay, this way, yeah. Yeah, so let's start with the surface. Surface lies in xy plane. Again, the flat surface lies in the xy plane. Let me draw it here. Right. So that's our surface. Maybe I even highlight it slightly. Okay. And dimensions, A, 2 centimeters, B, 3. And electric field, of course, must be given. So surface is a rectangle. Electric field is given in this form. E equals 100 times I hat. Again, you remember what is I hat? It's a unit vector showing positive direction of the x-axis, right? I hat. Then minus 200 k hat. K hat, unit vector in the positive z direction, right? And of course, units, newtons per coulomb. So that's the electric field, that's the surface. And again, the same question, what's the electric flux? Right, so we need to find electric flux, phi, Greek, capital Greek letter phi. subscript, I started adding subscript E because again, in a month and a half, maybe we will introduce magnetic flux, and of course I will be adding letter subscript M, which would stand for magnetic, but here electric flux, right? All right, so again, flat surface. This field, is this field uniform? Usually I ask this question, right? And first, some students kind of not very confident, right? So now it consists of two numbers, two components, right? So some students are not very confident answering this question. Is this electric field uniform? It is. It is, because magnitude is the same. You can calculate magnitude easily, right? Components are given. So magnitude is the same, and of course direction is the same. Right? There are no any dependencies of x, y, z, or time, right? So it's a uniform electric field. So we have flat surface, uniform electric field. So we still can use this formula, right? We can still use the formula E dot A. So again, E is uniform. Area is still flat. So we can still use the simplest possible formula, which is the E dot A. Right. Okay, and now, of course, which option to use? Again, dot product, scalar product, so which, this or that? Again, you can use both of them, but the second option is easier. And actually, that's why I picked this problem. First problem is designed to play with this formula for the scalar product. The second problem is designed to play with that definition. I mean, not definition, with this option of calculating the electric, the scalar product. So now we will use EX AX plus, so we'll just use product of components right. So no problems with the electric field. The electric field is given explicitly, so no troubles, right? So we can plug that immediately. So we just need to find components of the area vector. And first, when I start asking again, so guys, give me components. 50%, start panicking. What to do in this case? All right, so first of all, we need to draw it. Picture simplifies tremendously, right? Even as I think I mentioned to you, right, this semester we were preparing the comprehensive exam for PhD students, right? And when I added pictures to the problems, and professor said, oh, it makes problem looks much nicer and easier to understand what happens in the problem, right? So let's draw it, right? And then, of course, it's much easier to see components of the area vector. Again, as I told you, you can draw either area vector up or down, because the rectangle lies in the xy plane, so it's either A up or down. I don't like down, right? Let's draw it up. But again, if you take it downward, it's not a mistake, right? It's not a mistake at all. But I prefer to have a positive attitude, right? So let's pick area vector upward. So this is my area vector A. And again, it must be perpendicular to the surface. That's how we introduce it. Right? Okay, and now, when I draw the picture, when I draw the vector, and if I start asking questions, so give me components now, yeah, much more students are much more comfortable giving me components. Right? Okay, let me. A equals. What's the x component? Since area vector perpendicular to the xy plane, area vector fully in the z direction only, right? So x component is 0, 0 times I hat. Y component again 0. Project it on the y direction, you will get nothing, right? You will get a dot, so y component is also 0. Right. And again, as I said, once I usually draw the picture, I draw the vector, then it's much easier. And z component is the whole vector in the z component. So z component will be what? A times b k hat, right? Okay, I wrote immediately area A equals to A times B because it is just a rectangle. Right, okay, now let's calculate. Okay, let me rewrite it quickly. And again, don't forget to convert to meters. Don't create crazy units, right? Which is difficult to use and difficult to digest, right? So 2 times, okay, maybe I will write here. 2 times 10 to the power of minus 2 meters times 3 times 10 to the power of minus 2 meters, right? So it will be 6 times 10 to the power of negative 4, right? So that will be a z component. So here it will be 6 times 10 to the power of negative 4. The units, okay, I will write here later. So it's just meters to the power of 2. Okay, so now we have everything. We have components of both vectors, E, A. So let me just write explicitly this line. So electric flux equals to EX, AX, EX 100 times AX 0, just multiplying corresponding components, X components, Y components, Z components. Then, what's the Y component of the area, of the electric field? It's not there. It means it's 0, right? There is no J hat. It means that Y component of the electric field is 0. So 0 times 0, because Y component of the area vector 0 as well, and plus what? Y component of the electric field negative 200. Don't forget about those minuses and pluses. They are crucial, important. Minus 200 newtons per coulomb. And z component of the area vector, all right, 6 times 10 to the power of negative 4 meters to the power of 2. Right, so the answer will be negative, it will be 0.12, right? Really? 10 to the power of minus 2, that 12, yeah. It will be 0.12 newtons times meters to the power of 2 divided by coulombs. Am I correct? Yeah. Oh, minus. I said minus, but I didn't write it down. But again, it's possible to get plus if I picked my area vector downward, if I pushed myself into that, which seemed to be not very convenient, if I pushed myself to choose that direction, flux would be negative. Right? So usually, as I told you, we have right now we have a freedom to choose the direction of the area vector this way or that way. But when we get to the Gauss's law, that freedom will disappear. Right. So that's the answer. And again, both problems were just designed to practice electric flux, calculations of the electric flux, and to refresh the scalar product. Because yes, it's a very, very common tool in mathematics, in physics, in science, everywhere. Right? So it must be refreshed. And again, usually the troubles are in finding the correct angle between two vectors. So be careful with that. The same rule is used to find the correct angle in the vector product, right? Cross product. Right, and now let's look at another problem. similar geometry we're going to see when we start practicing Gauss's law. Right? Most likely tomorrow I will introduce Gauss's law and we will start looking at examples. Okay. So over here in the first two problems we had just a single surface, simple, a flat surface. But what if we have a surface more complicated? I couldn't find anything better except for this cylinder, right? Which is to clean carpet, right? So let's assume that we have a cylinder and exposed to a uniform electric field. And we will need to find the total flux through this complicated surface, because now cylindrical surface is significantly more complicated than flat surfaces, right? So let's calculate the electric flux in this case. Okay, so now it's time for me to clean that side of the board. Okay, we'll keep the last line still. This is problem 16a. Again, we solved for part A. In your homework, you're going to have A and B, right? I assigned the same problem as homework problem. So it's a 24, 16a. Right? So now we have a cylinder. So now we have a cylinder and uniform electric field. Uniform E. Okay, so let's draw the picture. I will draw the cylinder first. Let me make it big. Something like this. Okay, too big. Right. So let's say this is my cylinder. Radius is given. I think it's just R. Right, radius is given. And which is exposed, the whole thing is exposed to a uniform electric field. I think it's this direction, yeah, this way. Uniform electric field. Oh, four lines should be enough. Okay, now I can erase this. And, yeah, we need to find flux. Right. So let me write underneath. So we need to find the total electric flux. So what do we have to do now? First of all, cylindrical surface is too complicated, but we can split it into three surfaces, which and it's easier to work with those surfaces. First of all, cylindrical wall. Then front facet on this front surface and back facet. So three surfaces. In a Gauss's law, when we're going to have a similar symmetry, right? We're going to do the same. Cylindrical surface can be split into three surfaces: S1, S2, S3. Cylindrical wall and two facets. Right? Okay, so now let me label them. Which way I should label? Okay, I use green. Right, so let's call this as S1 cylindrical wall. It's that one, cylindrical wall. Then let me label this as S2 front facet. This side, front facet, right, S2, and then the back facet over here, S3, so back facet. So split into 3 parts because we're going to calculate flux, and flux is additive. Right? So if you calculate flux through one surface, flux through the second surface, flux through the third surface, then you can add them up. If you add them up, that will be the total flux through all 3 surfaces. So that's what I'm trying to do. Right? So now I can write that the total flux will be equal flux through the surface S1 cylindrical wall plus the flux through the front facet, and plus electric flux through the back facet. Now subscript E I dropped because too many subscripts in this case. It's not needed at all. Right? So now let's look separately at each of these fluxes. So let's start with S1. Right, so let me do it underneath. Flux through the surface S1, so the wall. First of all, we need to decide which formula can be used, or should be used, or have to be used. All right, cylindrical wall. It's no longer flat surface. I don't have to convince you in that, right? It's not a flat surface, period, right? So, it means that we no longer can use this formula. So we have to use that one. Everything is fine. All right, so we have to use this formula, which again, calculus 3, strictly speaking. But we will see that in this case, it's not that bad at all. All right, so integral of E dot dA. Because now it's not flat. Okay, let me emphasize that S1 is not flat. So that's the major, so the feature of the surface S1. And again, as I said, this integral is far from being trivial. In calculus 3, you will spend quite some time learning how to integrate over a surface, over a line, over a volume. Actually, it's fun. I remember I like that. But now let's look carefully at E dot dA. Let's look at the integrand of what is inside of the integral. Let's draw dA. What is dA? You just basically, like I drew over here, you slice the surface into many small patches. And take one patch, and let's draw the dA for that patch. So which way I would slice it, right? So of course I would slice it them vertically and then sort of like horizontally, and I will end up with, let's say, let me draw, this is one of those patches. It's like over here, if I take this small patch, you see even I try to highlight it. So my small patch. And if I draw area vector, it will be perpendicular, it will be radially, right? The area vector will be radial to that patch. So it will be this, my dA. And now, what's the direction of area, or not area, where is my, yeah, here. What's the direction of the electric field? Electric field horizontal this way. dA straight up. Okay, let me again use my cylinder, right? So effectively, we have dA that way, electric field that way. So what's the angle between them? 90 degrees. 90 degrees. What is cosine? Over inside of this, there is a cosine of angle, cosine of 90 degrees, 0, of course. That's why we can handle this integral easily, because if you look carefully at the integrand inside of the integral, you will see you're integrating basically zeros. Again, what is fancy? Integration is just a fancy word for adding small things. All right, so okay, so let me finish this quickly, right? So since E perpendicular to dA, so it means that theta is 90 degrees. Okay, 90 degrees, and now let me write it explicitly. So it will be integral of E dA cosine of 90 degrees, and the cosine of 90 degrees is 0. So the whole thing is 0. So the first integral is 0. The other two are, it's basically our previous cases, right? Those should be simple. Those should be simple. Let me quickly write it down. So now, those two flats, right, so through S2, except for, again, look, what's the direction of the area vector? Now it's a flat surface, and the area vector is that way, and over here, that way, right? So I can draw over here, so this will be my area vector for this surface, and this will be the area vector for that surface, right? And what's the angle? Okay, so phi through S2, it will be E dot A. So it's a E, A, and cosine. What's the cosine of, what's the angle? Electric field points that way. Area vector points this way. The angle is 180 degrees. Cosine 180 degrees is -1. So you will get minus EA. The flux in terms of electric field and the area vector. And flux through that back facet, exactly the same except for the angle. No, actually, yeah, it's S2, it's S3. It will be again EA and cosine. Now for that surface, you see on the picture, area vector that way, electric field also that way, the angle is 0 degrees. Cosine of 0 degrees, cosine of 0 degrees is 1. So it will be EA. And you will see, and you see what's the answer eventually. This is minus EA, that is plus EA, the answer is 0. In your homework, there will be very similar situation, but electric field will be split into two parts in two directions. Oops, it's a minus EA and plus EA, minus EA and plus EA. So the answer is 0. So what does it mean 0? It means exactly the same number of electric field lines entering this cylinder and exactly the same number of electric field lines leaving the surface, leaving this cylinder. Wait, sorry, there will be a very similar problem in your homework, part B. So of course you will have to repeat this one more time, part A, and there will be part B. Okay, so this stuff is not complicated, right? Usually students don't struggle much, right? And again, don't be afraid of surface integrals. Yeah, they're complicated, but over here we don't need that complication, right? So we just need to look carefully at them. Okay, so yeah, sorry for holding you. I thought I would be able to finish this, right? And I didn't want to skip it. Okay, so if you have any questions, okay, you can ask. If not, then I'm sure that you have other classes, right? And so next lecture tomorrow, we will use this idea of the flux.